Hi there, and welcome to our Chapter 10 problem solving video. We're going to go through one of every type of problem in Chapter 10. We're not going to go into too much depth, but we're just going to kind of gloss over everything. So first, we're going to cover Lewis structures. The beginning of a Lewis structure is the Lewis dot structure. And so the dot structure is just the number of valence electrons in that element. And so the valence electrons are just the amount of electrons in the very last row of that element. So phosphorus is in the third row. And so we would count how many elements are in that row. Or we can just look at the group numbers. If we have a nice periodic table, it will give us two group numbers for 13 through 18. It'll give us 13 through 18 as well as 3A through 18A, or 3A through 8A. Sorry, apologize about that. The number on those groups is the number of valence electrons. So group 1 has 1 valence electron, group 2 has 2 valence electrons. Group 3A, or 13, has 3 valence electrons. Group 14, or 4A, has 4. 15, or 5A, has 5. 16, or 6A, has 6. So forth and so on. So phosphorus is in the 5th group, so it's going to have 5 valence electrons, just like nitrogen. So we would draw the Lewis dot structure like this. We can take these Lewis dot structures and combine them between elements. Now, I typically won't have you do ionic structures, but it's in the book. It's something you might see in other classes. Other professors definitely assign it. I don't find the value in it. I'm not going to really assign these as quiz or exam questions, but we'll review them. Essentially, we know that ionic compounds give or take up their electrons. So in this case, magnesium is going to give up all of its electrons, and oxygen is going to take all the electrons. We'll represent magnesium with an empty shell. It has the full previous valence shell, but its current valence shell is empty. And oxygen is going to have its current valence shell full. Magnesium will get the +2 charge, oxygen will get the -2 charge. Whenever we have an ion in Lewis structures, we want to make sure that we put a bracket, not a parentheses, and the charge in the top right corner. All right, so we could do this with calcium chloride. However, we know that there are two chlorines for every one calcium, because calcium is going to take a +2 charge based on where it is on the periodic table, or based on how many valence electrons it has. Same idea. You can look at it either way. And chlorine is going to gain 1 electron. So you're going to need 2 chlorines to gain the 2 electrons calcium's trying to give up. When we do this in an ionic structure or an ionic covalent structure, ionic Lewis structure, we represent them evenly spaced around the calcium. Typically, we'll do it horizontally rather than vertically, but if you prefer to do it vertically or the page allows for vertical alignment, then totally fine. We just want to evenly space or symmetrically space these things around. So 2 chlorines around calcium, we can arrange them in a line as the most evenly or symmetrically dispersed. So moving on to the more important types of Lewis structures is covalent compounds. Now, I've mentioned this. I have my preferred way of doing Lewis structures. The book has its way. The book's way is a very common way. I recommend that you use a slightly different rule set, and I'll go over that in just a moment, but we'll go over the book's rules. So you always want to come up with a skeletal structure. This is true for both methods. The way that you figure out what your central atom is going to be is whichever one there's the least number of. In this case, there's only one atom that is the least amount of it. So carbon's going to be our central atom. But if we had, multiple atoms that only had one atom represented in that chemical formula, we would choose the one that's the least electronegative and not hydrogen. Hydrogen can only make one bond, so hydrogen can never be the central atom. So too with the halogens, but the halogens are usually more electronegative than what they're bonding to, so not as common as an exception. So we'll put carbon in the middle, evenly space oxygens around them. Anything that's 2 or 3 bonds or atoms is going to take the linear structure. Remember, I want you to memorize the linear structure, the bent structure, trigonal planar, trigonal pyramidal, and tetrahedral. Those structures and their idealized bond angles are what you should know, with the exception of bent, because the bent geometry is purely dependent on how many electron pairs you have and what atoms you have. Now going back to carbon with our central atom and oxygen being our evenly spaced auxiliary atoms, we want to count the total number of electrons in the valence electrons. So oxygen would have 6 valence electrons. We have 2 oxygens, so 12 valence electrons. Carbon's going to have 4 valence electrons, so 12 plus 4 is 16. We then want to space those electron pairs between the bonding elements, so between carbon and oxygen and carbon and the second oxygen. Then we'll fill the electrons around the most electronegative atoms first, and then the central atoms or less electronegative atoms if we have extra electrons. In the case of carbon dioxide, we don't have extra electrons, so we're going to have to share a pair of electrons. Now, this works really well when you have nice, simple molecules. Carbon tetrachloride is an example of that. So if we put first count the number of electrons. We know carbon's going to be the central one because carbon is in the middle, or there's only one carbon and there's 4 chlorines. We can surround the carbon with 4 chlorines. We can look at their valence electrons, sum them up. We'll get 32 valence electrons. And we can fill them in between carbon and the chlorines first, and then all around chlorines, and we actually have the perfect structure. So this is nice and well for easy, simple structures. However, once you get to more and more complicated structures that maybe have exceptions to this rule, you'll find that it might be easier just to put the total number of valence electrons on each element once you've organized them into the proper geometry, just like we did in the first step here. Give carbon 4 electrons, give chlorine 7 electrons for each chlorine, and then pair their unpaired electrons. That doesn't have as many exceptions to those rules of pairing electrons, but either one's fine. I'll go over both of them in the lab as well as in office hours. So you could try to draw the Lewis structure for formaldehyde. Formaldehyde is going to have a double bond between oxygen and carbon. Hydrogen always makes single bonds. And so what you'll find is that certain elements will make a certain number of bonds. So hydrogen will always make 1 bond. Halogens, fluorine, chlorine, iodine, and bromine will always make 1 bond. Oxygen will either make a double bond or 2 single bonds. Nitrogen will make a double bond and a single bond, 3 single bonds, or a triple bond. And carbon always wants to make 4 bonds. However, it can do that with the arrangement of single, double, and triple bonds. That's what carbon's going to do. Carbon will never have lone pairs. Nitrogen will almost always have 1 lone pair. Oxygen will almost always have 2 lone pairs. And our halogens will always have 3 lone pairs. So, there will be a couple exceptions. We'll cover them if they matter in later chapters. We don't care about those exceptions right now. So, we could do polyatomics just as well. The thing that we have to be careful about with polyatomics is that they have a charge. Same as ions. Ions have charge. We have to add or subtract a certain number of electrons. So for ammonia, we would take away 1 electron. When you take away electrons, you want to take them away from the least electronegative atom. The atom that's going to be easiest to take that electron away from is the electron that's most likely going to get that, or is the element that's most likely going to get its electron removed. So in this case, it's going to be hydrogen. So we could put up all the valence electrons and then remove 1 from hydrogen, connect all the unpaired electrons, or we can do it the book's way where we count up all the electrons, place bonding electrons between all of the pairs, and then fill in any extra electrons. We only have 8 electrons because nitrogen has 5, 4 hydrogens each have 1, but we take 1 away from the hydrogen, or if in the case of the book's way, we don't have to take it away from any element. It's just we don't give it to an element in the first place. And we'll notice that we have exactly the right amount of electrons. Nitrogen has its octet. Hydrogens all have their duet. Whenever we write these structures, it doesn't matter if we put lines between them or if we put the dots, but we want to put a bracket and the charge. Otherwise, someone's going to assume this is neutral. Now moving on to resonance structures. Resonance structures are just equivalent Lewis structures or identical Lewis structures for atoms that have multiple bonds between atoms of the same type.
So in this case, we have nitrogen bonded to 3 different oxygens. If we do our Lewis structure for this, counting up all of our electrons, putting the electrons in between there, and then doubling up to get any double bonds. Again, I would put our valence electrons down first, then connect any unpaired electrons and add our extra electron to the most electronegative atom, one of the oxygens. And that would give you the same Lewis structure. But once we get our Lewis structure, we have this question of which one gets the double bond. Does it have to be this one? Can it be this one? Could it be this one? The answer is any one of them is correct, and all 3 of them are actually true. And so what we have is called a resonance hybrid, where this molecule nitrate, the polyatomic, actually looks like a combination of 3 different resonance structures. So we could draw this as any of these 3 versions. So up top we show that technically these 2 are the same by symmetry, and that's fine, but realistically we have 3 different Lewis structures. Each one of these is correct, and the molecule is actually just a combination of all 3 of these at any given moment. So you could practice this with nitrite. It's going to have a similar thing. Nitrogen is going to be bonded to one of the oxygens with a single bond, one of them with a double bond. You can't have resonance with just single bonds. That's called a saturated molecule. Saturated molecules don't have any resonance. So we can take this a step further and look at molecular geometries rather than just the Lewis structures. And so the Lewis structures give us kind of like a 2-dimensional connectivity of how these molecules are. And so here we can see the 2-dimensional representations of a few molecules we've talked about, and then the 3-dimensional ball and stick or space filling models of these molecules. And so you see that some of them, linear, trigonal, planar, even bent, are very well represented by the Lewis structures. However, trigonal, pyramidal, tetrahedral, and the more and more complex geometries are not really represented well by Lewis structures. So we have the VSEPR model that kind of influences how different electrons group together and push each other away from each other. And so we have these, 4 or 5 different geometries that I'm making you memorize. So we have linear. When we have 1 or 2 things bound to a central atom, we're typically going to have a linear as long as we don't have any lone pairs on that central atom. If we have lone pairs on that central atom and we're bonded to 2 things, we'll have some type of bent geometry. Now, the angle of this bent geometry depends on how many lone pairs. In water, we have a really tight 109-degree angle between these 2 hydrogens because there's 2 lone pairs pushing them down. Again, the lone pairs exert a larger area or a larger force on the molecular geometry than the bonding pairs that are shared between 2 atoms. So in sulfur dioxide, we see a smaller 120-degree angle between these terminal oxygens, whereas these terminal hydrogens, it's 109.5. I'm not going to make you memorize the bent angles, as it purely depends on what the terminal atoms are and the lone pairs. But I do want you to know the idealized geometries for linear, trigonal planar, tetrahedral, and trigonal pyramidal. Trigonal pyramidal is, essentially just the same as tetrahedral, but we're missing a bonding pair and we replace it with a lone pair. That's the only difference between trigonal and tetrahedral. The difference between trigonal pyramidal and trigonal planar is that we have this extra lone pair. In formaldehyde, we don't have a lone pair. In ammonia, we have a lone pair. And so this lone pair is pushing those extra or terminal hydrogens down and kind of puckering the planarity, forming this pyramid shape. So we could, approximate what the molecular geometry of this molecule is. Nitrogen would be our central atom. It's told to us, but it's the least electronegative one. And it's, all of them just have 1. So you pick the one that has the least number of atoms and is the least electronegative. They're all the least number of atoms. Nitrogen is the least electronegative. We pick nitrogen. Chlorine isn't even a candidate because halogens can only make 1 bond. So really it was only between nitrogen and oxygen. So if we saw this, nitrogen bonded to 2 things. Nitrogen's probably going to have a lone pair. It's probably going to make 2 bonds to oxygen, 1 bond to a halogen. It's probably going to look something like sulfur dioxide, but you can play around with the Lewis structure and solve for yourself and convince yourself of that. So for nitrate, we've kind of already know this, but using our VSEPR theory, we don't have any lone pairs on nitrogen, so we're not going to distort the geometry around this. So we're really just going to idealize the geometry. And so this would be our trigonal planar molecule. The book just has their steps. You can pause and read along with those. But at the end of the day, we kind of always want to reference this table if we're unfamiliar with the geometry. Again, carbon, nitrogen, and oxygen, I'm going to want you to be familiar with their geometries. Carbon bonded to one or two things is linear, to three things is trigonal planar, four things is tetrahedral. Oxygen bonded to water or bonded to hydrogen makes water. That's our bent shape. Nitrogen bonded to three hydrogens is ammonia. That gives us our trigonal pyramidal shape. Besides those, we can look at a table like this. There's an extended table that, goes to all the different complicated geometries like seesaw, T-shape, and trigonal bipyramidal, and all sorts of other various nonsense that we don't really care too much about. So next, we're going to move on to bond polarity. This isn't going to be something that I'm going to ask you questions on. There will be a couple questions in the book homework and on exercises, things like that. This is more something you should understand conceptually, because in order to do this mathematically, you have to have the electronegativity values. Maybe you will memorize fluorine as 4 because that's what the scale is based off of, but pretty much every other one, I wouldn't even expect you to memorize fluorine. So I would have to give you these values, and then you'd do a simple subtraction problem. You'd rate this against a scale that would be given to you, and that's not very useful. What I want you guys to see, or to identify, is whether or not things are going to be on extreme ends of the polarity scale. So our polarity scale can be essentially broken up into perfectly covalent, which is where you have no difference in electronegativity. The only way we get that is if two elements of the same type are bonded to each other. Oxygen bonded to oxygen in molecular oxygen, or hydrogen bonded to hydrogen in molecular hydrogen, or any of the molecular halogens. Those are all perfectly covalent compounds. After that, we have some level of nonpolar to polar covalent. The more ionic they are, the bigger the difference in electronegativity, the more polar they're going to be, or the more ionic like they're going to be. After you get, about a difference of 2 electronegativity units, or polyelectronegativity values, you're going to call it ionic classically. So in this case, strontium and fluoride are going to make an ionic compound. Nitrogen and chlorine are real close to each other, just like nitrogen and oxygen. Nitrogen and oxygen are a little bit bigger, or bigger difference in electronegativity. However, they're closer together, and so I wouldn't expect you to know that difference without having a table that you could reference. Nitrogen and chlorine have almost the same electronegativity. This would be a very nonpolar bond, where this would be a very minorly polar bond, and this would be a ionic bond, or incredibly polar bond. So we can just look at this and do the mathematics for everything. So nitrogen has a 3, oxygen has a 3.5, so a 0.5 difference. That's technically a polar covalent bond according to our classification scheme, but it's just barely over the threshold. 0.4 is the cutoff for the threshold, and so technically it's a polar covalent bond. If we look at chlorine and nitrogen, on this scale, it doesn't give us enough decimal places, but nitrogen and chlorine are the same, and so we would call that, perfectly covalent or non-polar covalent. It's not truly perfectly covalent. Chlorine, I believe, is a little bit more electronegative than nitrogen by a couple decimal places, but it could be the other way around. I honestly forget. Doesn't matter. You guys don't have to reference it. So this is our classification of what, non-polar or pure covalent, perfectly covalent, or idealized covalent is. It's pretty much our diatomics. That's the only thing that really falls into this classification. We have, our covalent bonds. The majority of our covalent bonds fall in some range of polar. We saw nitrogen and oxygen. That's very moderately polar, but it is polar. Hydrogen fluoride, something that has a electronegativity difference of 1.9. is almost over that scale. It's almost to the ionic scale, so it's very, extremely polar covalent. And then something like sodium chloride or fluoride or any alkali metal, halogen, or oxide is going to be extremely polar and thus ionic. So you could classify all of these again. So we have iodine, iodine. Again, if they're exactly the same, it's going to be perfectly covalent. If we have different elements, especially if they're on opposite ends of the periodic table, we're going to have ionic compounds. We're going to have extreme differences in electronegativity. We're going to have a very polar compound, so polar that we have isolated positive and isolated negative charge. Cesium bromide. Cesium is in the bottom left. Bromide's kind of in the mid right of the halogens. This is a very polar compound. It's ionic. Phosphorus and oxygen, little bit of difference between them. We have about a 1 electronegativity difference between them, or delta En. And this is going to be what we would call polar covalent. This is going to be the end of our problems. And if you have any questions, make sure to reach out or see me in lab.